In the first video, we have seen the mathematical relation, that is that when we connect two LTI systems in parallel, their impulse responses are added, right? So connecting two LTI systems in parallel is equal to adding their impulse response. In this particular video, we are going to analyze why it is true, how we reached into that result. This can be either proved mathematically or experimentally. If you can do some experiments in MATLAB or Python language, you can prove this, right? But here in this particular video, we are trying to analyze it mathematically, how we reach to this result. Why connecting two systems in parallel is equal to adding their impulse response. So without wasting time, let us go into the video and watch why it is true.
In the previous video, we have just analyzed how the LTI systems will interact in parallel and cascaded connections. Now let us analyze it in a deep manner, right? So let us go further into the system and let us analyze how it will behave, right? So let us assume that h1 of t is the impulse response of the first system S1 and h2 of t is the impulse response of the second system S2. So let us call it as S1 and S2, and I am giving an input x of t, right? What happened to the x of t? It will be split into two in the parallel connection and it will come here, right? Both of the inputs are x of t here, right? Now if you give like that, what happened? You will get some output from the first system. So let us call it as y1 of t, right? So this is y1 of t and this is y2 of t, right? y1 of t and y2 of t. So what happens at the output is that they will be added together and you will get y1 of t plus y2 of t, right? y1 of t plus y2 of t. So this symbol should be addition symbol. So this is a adder. Actually it is an adder, so that will be added and you will get the output. So from this understanding we can actually develop a analysis, right? So let us write the equation y of t is equal to actually y1 of t plus y2 of t. Y of t is equal to y1 of t plus y2 of t. So in that we know that y1 of t is actually what? It is the interaction between the signal x of t and the impulse response h1 of t, right? So what interaction? It is convolution interaction, right? And what about y2 of t? Y2 of t is the interaction between the same input x of t and h2 of t. So what interaction? That is again convolution, right? Now we know that this is y1 of t and this is y2 of t, right? Now if you substitute this y1 of t and y2 of t into this equation, our main equation, so we can derive an expression or the proof for the operation of LTI systems in parallel, right? So let us substitute that into the equation. So you will get like this: x of t convolution h1 of t plus x of t convolution h2 of t. So this is actually nothing but y1 of t, this is y1 of t and this is y2 of t, right? So we are adding them together. Now we express them in convolution integral. Actually this is convolution symbol here, so instead of convolution symbol, if we express them in convolution integral, you will get like this. What is the convolution of the first two sequences? It is integral minus infinity to plus infinity x of tau into h of t minus tau d tau, right? So this is the first one. So plus, what is the second one? The second one is given as integral minus infinity to plus infinity x of tau into h2 of t minus tau d tau, right? So here it is h1 of tau. I forgot to write it. Actually it is h1 of t minus tau, right? If you look into this equation, you can see that you can take these things common, that is minus infinity to plus infinity x of tau is present here. The same minus infinity to plus infinity x of tau is present in the second part of the equation also. So we can take them together. So if I take them together, I can write it like integral minus infinity to plus infinity x of tau. So I am taking that in the outside, and inside the bracket I will write as h1 of t minus tau, right? h1 of t minus tau plus h2 of t minus tau, right? So this term and this term, right? So I will close the bracket and I will write d of tau. Now if you define something, what if you define, if suppose, right, if you define h1 of t minus tau plus h2 of t minus tau equal to h of t minus tau. Then this equation can be written as, the above equation can be written as, how can you write? We can write minus infinity to plus infinity x of tau into h of t minus tau, right? So this is nothing but x of t convolution h of t, right? So what is the meaning of that? Actually, if we consider the overall system response h of t as a sum of individual impulse responses, then we can write like this. So from this, what is the conclusion? We can conclude that the overall system response in a parallel connection is equal to the sum of individual impulse responses h1 of t and h2 of t, right? So we can replace the diagram. So the diagram which we have drawn at the beginning of this analysis like this, from this result, how can we analyze, how can we write it? So I will just draw a box. So this box is the overall system, right? This box is actually the overall system, and this is nothing but h1 of t plus h2 of t. Actually we are adding the impulse responses inside, and together we can call it as h of t, right? And if you give the input x of t, if you give the input x of t into this connection, you will get y of t, right? So instead of connecting them in parallel, right, connecting two systems with h1 of t and h2 of t parallel, see this is h1 of t, this is h2 of t. Instead of connecting them in parallel, we can add the impulse responses of h1 of t and h2 of t inside the system, and we can give the input x1 of t to obtain the same output y of t. So here what you have done, so here what you have done, here you have given x of t separately to the systems, and you take the output y1 of t and y of t separately, and finally you will add them together to get y of t, right? The same thing can be achieved by adding the impulse responses together and giving the input x of t, you will get y of t. So this y of t and the previous case y of t will be same, right? So the basic idea is that if we have a parallel connection of LTI systems, instead of giving input separately to the systems, you can add the impulse responses of the systems and you can give a single input to get the overall output. That is the basic idea of parallel connection, right? So we can conclude that impulse response of overall system represented by two LTI systems connected in parallel is a sum of their individual impulse responses. Once again I will repeat, the impulse response of an overall system represented by two LTI systems connected in parallel is a sum of their individual impulse responses, right? So we can write two expressions here. One expression is x of t convolution h1 of t plus x of t convolution h2 of t. So this is the parallel connection representation, is equal to x of t convolution sum of h1 of t and h2 of t. So these two are equal. So this is the basic result we derive from this idea. And if you consider the discrete time case, how can we write? If the signal and system are discrete time, then we can write it as x of n convolution h1 of n plus x of n convolution h2 of n is equal to convolving x of n with the sum of h1 of n and h2 of n. So this is the basic idea which we derive from this parallel connection. So you have to keep this in mind. This is how we derive an expression for the parallel LTI systems.
I hope you got a clear idea about connecting two systems in parallel, right? So please don't forget this: connecting two systems in parallel is equal to adding their impulse responses and creating a system whose impulse response is the sum of the two impulse responses of the subsystems, and then give the input, you will get the output, which is equal to parallel connection of the LTI systems.